Hello everyone, this is Chengzhi Wu from Karlsruhe Institute of Technology, Germany. It is my pleasure to present our work of SynMotor, a benchmark suite for object-attribute regression and multitask learning. The whole presentation will be divided into 5 main parts, namely, the motivation, the pipeline for generating the dataset, the benchmark tasks and metrics design, the baseline results we provided, as well as the conclusion and outlook. In the past decade, many novel network models and algorithms in the machine learning field have been proposed. To evaluate and compare the performance of various models, datasets and benchmarks are playing a more and more important role. A good dataset can boost the development of a certain computer vision domain. For example, Pascal and Coco have been widely used as benchmark for 2D object detection, ShapeNet and ScanNet are being used for 3D segmentation. And Kitty is an important benchmark for 3D detection in the autonomous driving area. However, among all the computer vision tasks, the task of attribute regression is less explored due to the scarcity of suitable benchmarks. Current attribute learning methods mostly focus on outdoor pedestrians or human facials, but most of these attribute annotations are binary. For example, the Celeb dataset offers the labels of gender, a face smiling or not, with glasses or not. On the other hand, regression models with neural networks are mostly used for non-vision data. We think it would be interesting if we could contribute to bridging the gap between attribute learning and regression for the computer vision community. In this paper, we propose SynMotor, a benchmark that gives the possibility to perform object-attribute regression. Multitask learning and multimodal learning are also possible with the provided dataset. The benchmark originates from a subtask within our manufacturing project, AgiProbot. The AgiProbot project aims for auto-detection, tracking and disassembly of end-of-life products. To be specific, in our current experimental setting, we work on small electric motors used in vehicle manufacturing. Universal method needs to be developed to deal with various types of motors, including the ones with unseen specifications. However, we are only provided with a handful of motors with only few different product specifications. The variance of data is actually not sufficient for training with machine learning methods, especially those deep learning-based ones. To deal with this problem, synthetic datasets are generated. The network models are first pre-trained on the synthetic data and then use Sim2 real transfer learning to fine-tune on the real-world data for actual applications. Let's see how we generate our synthetic dataset. Based on the motor templates we have currently, we created a Blender add-on named Motor Factory, which can generate motor mesh models with a variety of specifications. In the middle is the explosion figure of a random generated motor model, and on the right are the motor models with or without additional textures. The generated models contain the following components: pull pot, electric connection, gear container, cover, side screws and cover screws. Those are the 6 main categories we need to perform segmentation on for the first step of disassembly. Additionally, the following inner components have also been generated: magnets, armature, lower gear and upper gear, as presented in the explosion figure. All the individual components mentioned above are modeled separately. To generate motors with various specifications, we provide lots of parameter options that control the type, size, position, and rotation of different parts of motor, like screw position, gear size, or pull pot length. Overall, our add-on is able to generate motor mesh models with various specifications and save them in desired file formats. Each component of a generated motor can also be saved separately. This enables the proposal of the attribute learning task. The generated mesh models are further used to create synthetic image and point cloud datasets. A simulated scene is built in Blender for it. Apart from the lights and cameras, to make the scene more realistic, a model of the real-world clamping system and a background panel have been added additionally. 3 light sources with random changes in light intensity are placed in the scene. The camera rotates randomly on top of the scene within a certain view range, yet always towards the motor. Blender Proc is used to generate RGB images and corresponding depth images, normal images, and segmentation ground truth images. Detection ground truth of bounding boxes of motor and screws are also provided. This is the workflow for how we generate the images. The rotation and position information of camera and motor are saved. Here are some demos from our image dataset. On the 3D synthetic data side, BlendSor is used to simulate the sensors to create point cloud data as well as to generate their segmentation ground truth. 3D bounding boxes are also given. Moreover, for better learning of key objects, we additionally provide corresponding subpoint clouds for each scene by cropping random cuboid regions around the motors, but make sure to include them. This is the flow of how we generate the 3D dataset. Here are some demos from our point cloud dataset. Here is the tree structure of our full dataset. We have created a synthetic motor mesh dataset of 1000 motor mesh models with different specifications. They are placed in the same simulated scene but with random camera settings, random light conditions, and random mild translations and rotations. With these 1000 scenes, 1000 sets of images and 1000 point clouds are generated respectively. 80% of the data are randomly selected as the training data, while the other 20% are used as the test data. To ensure the correspondence between images and point clouds for each scene, the camera information has been saved and shared between Blender Proc and BlendSor. As mentioned before, our datasets provide the specific geometric attributes information and ideal for attribute learning. 30 attributes are selected and used for the task design, as given in this table. Attribute type and number of cover screws are suitable for classification tasks, while other 28 attributes are suitable for attribute learning. Figure on the right shows the selected attributes on the motor. They are, the length of the bottom part, the length of the sub-bottom part, the diameter of the lower gear, the diameter of the upper gear, the center location of the lower gear, the center location of the upper gear, the center locations of the cover screws, and the rotation of the motor. Note that some attributes are invalid in some cases, for example, the XYZ coordinates of 5th cover screw when the motor only has 4 cover screws. While the attribute values are set to 0 when they are invalid, an additional binary mask CSV file is provided for all 28 attributes of all 1000 motors. In our benchmark, all 28 attributes are continuous variables, hence are suitable for attribute regression. Now let's move to the benchmark tasks and metrics design. Classification and segmentation are common computer vision tasks. All those tasks can be performed on 2D and 3D level. Classification is to classify motor type and segmentation is to assign a label to each pixel or point. We use classification accuracy as the evaluation metric for classification task, and overall IOU and screw mean IOU as segmentation metrics. For the detection tasks, the ground truth bounding boxes are provided. The widely used mean average precision was originally proposed in the VOC challenge. We use an advanced version in Cocoa which further considers different IOU thresholds. For the attribute learning, we regress the values of 28 attributes and define 6 evaluation metrics considering on multi-perspectives, including object size, object orientation, and object keypoint positions. It is worth noting that since the attributes are not always valid in all scenes, a binary mask is used for the metrics to get more accurate error information. In the following definition of each metric, for a clearer description, we use A to denote the union set of involved attributes, with a corresponding binary mask MA. Size relative error evaluates the predicted overall motor size using 4 key attributes which represent the main body of motors, the length of the bottom and the sub-bottom part, pole pot, and the diameter of the gear regions. Gear location error evaluates the distance error between the predicted location of gear region center and its ground truth. We further provide another metric that only considers the distance error on the XZ plane with projected points. Motor rotation error evaluates the absolute motor rotation error, and screw location error evaluates the distance error between the predicted cover screw locations and their ground truth, same as gear location error on XZ plane. The screw location error XZ considers the XZ plane. Moreover, apart from the above separate tasks, multitask learning or even multimodality learning are also possible with our dataset. We use some widely recognized network models of certain tasks to get baseline results for the benchmark. This is the framework of our whole experiments, including dataset generation, 2D detection and 3D classification, segmentation and attribute regression. We will go into more detail later. For the detection task, we give baseline results on 2D image dataset. The well-known YOLO models of different sizes are used. The table shows the YOLO framework achieves remarkable performance on detection tasks. The map performance also improves and a larger network model is used. For 3D classification and segmentation tasks, we use DGCNN as the network backbone to produce baseline results. For the classification task, the global feature is processed with several followed dense layers to get a classification prediction, while for the segmentation task, the global feature is repeated and concatenated with pointwise features to process through several other dense layers to predict pointwise labels, as shown in this figure. Note that although two tail blocks are different, the encoder block is identical. It is possible to use a shared encoder for both classification and segmentation tasks. In this case, by adding the losses together and performing gradient backpropagation at the same time, we can train on the classification task and the segmentation task simultaneously. This is a simple way of performing multitask learning. The red line indicates how the information flows during one training step. The encoder block is co-trained with both tasks, while the respective task tail blocks are trained in parallel. Baseline results are given in this table. DGCNN is also used as the backbone for attribute regression learning. We consider the classification and segmentation as a metablock, and the regression tasks compose a second tail block. With the proposed architecture, there are several possible ways to train those blocks. The first one, totally separate training, the encoder and the metablock are trained as one network first, and then another same structure encoder and the regression block are trained as another totally separate network. No information is shared between two trainings. The second one, use metablock for pre-training. This method is similar to the last one, but the encoder weights in the second step will be initialized with the weights from the first step. The metablock is used for pre-training. The third one, encoder shared yet tail blocks trained in parallel. The encoder is shared between two tail blocks and three blocks compose one joint network. All tasks are trained in parallel. The fourth one, encoder shared and tail blocks trained iteratively. In each training step, the encoder is firstly connected with the metablock. We compute the loss, perform gradient backpropagation and update model weights with these two blocks. Then the same encoder connects with the regression block in a switch manner. The input is reprocessed with the weight-updated encoder to get new encoded representations which are used for computing the regression loss. We then again perform gradient backpropagation and weight update in these two blocks. This action performs iteratively. The red lines in the figures indicate how the information flows during one training step. The results are shown in Table 4. In most cases, performing attribute regression with semantic segmentation decreases the regression error. Regression can also help in determining the number of cover screws. Among them, the pre-train-based method significantly improves the regression results and the iterative training approach achieves the best results for segmentation. There are surely some other better ways for better results. We would like to leave this as an open question for other interested researchers. To conclude, in this paper, we propose a benchmark using synthetic 2D and 3D dataset, in which motors are the key objects. Motor attributes are saved during the dataset generation and are suitable for the less explored attribute regression task. Several evaluation metrics are designed especially for the regression task. Baseline results on several tasks are also provided. We hope this work would contribute to the attribute regression or multitask learning domain in the computer vision community. Thanks for listening.